Okay, continuing to work with exponential functions, we're going to examine exponential growth and decay problems. Now, these are modeling real-world situations, and they're going to involve this growth or decay, which we're going to find out is using explicit exponential functions. They are generally the same format, but the difference is going to be in the value of our base. So, as some of the things that we've talked about is the exponential function looks like this. Y equals ab to the x power, and b is my base. A is my initial value, b is my base, and x is going to be the amount of time the amount of times that something is changing. So looking at that, looking at my base, exponential growth is going to be when my base is growing. It's greater than 1. And then exponential decay is going to be when my base is continually decreasing, or it is the value less than 1, where we are constantly creating a smaller proportion of it, or a smaller ratio, not ratio, a smaller item of it, a piece of it. For example, if we take $1 and we take $2, starting off at $2, and we cut it in half. The first time we cut it in half, it's $1. The second time we cut it in half, it's 50 cents. The third time we cut it in half, it's a quarter. That is decaying because we're taking less than what we started with each time. So, but we'll examine these and we'll work with it. But exponential function, I think, will be easy to recognize and work with just a little bit of practice. So going forward here, modeling exponential growth, suppose that in 1985 there were 285 cell phone subscribers in a small town, and then the number of subscribers increases 75% each year after 1985, and then how many cell phone subscribers were in the small town in 1994, and write an expression to represent the equivalent monthly cell phone subscription increase. Okay, well, they gave us information from a year because they're saying it increases 75% in a year, but they're asking us to write an equivalent monthly subscription increase. So those are some things to consider that they've mixed up for us. But if we look at our original y equals a times b to the x power, knowing that a is my initial value. So it says right here that in 1985 there were 85 cell phone subscribers. So there you go. I'm looking right here that 85 is equal to a. That's my initial value that I'm starting off with. So I start off with 285 people. And I'm going to be multiplying that by the original value, or what I started with, which is 285. So that would be, if I looked at that, that would be 100% of that original value plus an increase of 75%. And I know I wrote that a little bit small, but 100% plus 75%. And that is going to be happening over X time. Now, X would typically here be in a year because 75% is occurring in a year. But we need to break that year down into monthly pieces. So when I do that, I'm going to have 285 times 1.75. Now, I turned 100% and 75% into a decimal, which is 1.75. And then, let's see here, X. Well, I know that 1 year is equal to 12 months. So I can take, if X is equal to 1 year is X, then that would be equal to 12 over 12X, breaking it down into my months. So that would be 12 over 12x would be my new exponent. And using the property, I can multiply my exponent properties, right? So I know that 285 times 1.75 to the 1/12 times, or raised to the power of 12x. Now that is going to identify this new growth right here. That is identifying growth in a month. Okay, So then when I multiply that out, that is going to give me 285 times 1.05, and this expression right here stands for a month. No longer a year, but a month is what I'm looking for, so it would be a month. And that is my monthly increase. Now, if I wanted to go ahead and, let's see, there's my write an expression that represents the monthly cell phone increase. There it is. Now, if I go ahead and solve that, I don't think they've asked me to do that, but I think I could go back here to this original problem, and I have 285 times 1.75. Now that's a year, right? So how many years has it been since 1985? Well, that would be 1986, 7, 8, 9, 10, or 1990, sorry. Then 91, 92, 93, 94. So it looks like that would be 9 years. So I could go back to that original problem based in years and come out that we have approximately 43,872 subscribers now. I don't think they asked me to do that, but hey, I could have figured it out. Okay, so as we move forward here, compound interest now. Compound interest is going to be a growth, and or compound interest should always be a growing factor, yeah, because you're compounding interest in it, your money is increasing. But if we look here, this formula, the amount is going to be equal to the principal times 1 plus r over n times nt, or to the power of nt. So P is going to stand for my principal. That's my initial value. So we have some value is going to be equal to P, which is the initial stuff that I put into my, and then it's going to be 1 plus r over n, and that is going to be my growth factor, because I'm accounting for my original 100% plus whatever rate I'm getting for my interest. And then the n is only in factor, just like up here. The n was only a factor when we had it something less than 1 year. So n is going to be something less than 1 year. Otherwise, it's going to be just the value of t, which is the time or the number of years. So looking at this, I can go ahead and say, okay, nt. Now it says, suppose that when your friend was born, your friend's parents deposited $2,000 into an account. Okay, and it pays 4.5% interest compounded quarterly. That would be awesome. You don't see that very much anymore, where you have something that's compounded greater than once a year. What will the amounts be after 18 years? Okay, well, they're asking me again for some amount, and that is the account balance, right, is going to be equal to the principal, which is the initial investment. So if I need to, it's A equals A times B to the X. So A is going to be the initial amount, my principal. In this case, my principal is the initial amount, which is $2,000, times 1 plus the rate. The rate is going to be R right here. That is my rate, 4.5%, which we should be able to say that that is 0.45 as a decimal. So that is going to be, so replace R with that decimal. So it's going to be 0.45 over N. Now I said that N is equal to the number of times greater, or the number of times that it happens within 1 year. You know, as I like to say, the happenings within a year. So it is happening quarterly, which that means it happens 4 times within a year. So we divide by 4. And then I have N is on the outside as 4. And then finally T. t is the number of years or the time, and that is going to be 18 years. And there you go, we've set our equation up. The initial value, principal of 2,000, multiply that times the 1 plus the rate divided by the number of happenings per year. So the rate was 0.045% divided by 4, raised to the power of 4 times 18, 18 being the number of years. Put that into the calculator, and I'm hoping that you get something along the lines of $4,473 or $75.53. So $4,475.53, and I rounded to the second decimal because we're talking about money. And if you needed to do that and verify your information, okay, so what I did was I just went ahead and multiplied my rate out and simplified my exponent to where I end up with $4,475.53. And if you plug the same thing in, it says, suppose that the account of interest is compounded monthly. What is the account balance? Well, monthly is going to be what changes here, and that is going to be the value of n. So n, instead of being 4, is going to be 12. So my amount would be equal to the original $2,000 that was invested, 1 plus my rate, which was 0.45, divided by 12, because it's now monthly instead of quarterly. And then we would have 12 times 18, and that gives me, again, let's see, it's going to be a little bit different. Let me put it in the calculator and see. Okay, so when I go ahead and multiply that out, I end up having the amount is going to be equal to 2,000 times 1.00375 raised to the 216th power, and that's going to give me $4,489.01. So just remember, when you're doing money, always round to the cents, let's see here. Moving forward, we've done 2 growth, so let's look at exponential decay. So that is when we are taking away, not just increasing greater than 100%, we are going to decrease by 100%, or from 100%. Okay, so a kilopascal is a unit of measure for atmospheric pressure. And the atmospheric pressure at sea level is about 101 kilopascals. For every 1,000 meters increase in altitude, the pressure decreases about 11.5%. And what is the approximate pressure at the altitude of 3,000? Well, okay, so we have a function, and the initial times the base raised to some power. So let's see here. We have what is the approximate pressure? So my pressure is going to be equal to the initial amount, which turned out to be 101 kilopascals, times the base. And the base they have given me is, well, pressure decreases about 11.5%. Okay, so we have 1, and since it decreases, we're not adding to it. We're going to be decaying and taking away. That is going to be minus 11.5%, which is going to be equal to 0.115 as a decimal. So we have the value of 100% of our stuff is going to be 100% minus the 0.115, and it's going to be raised to the power. Well, we know that x is going to be equal to 3, or x here is going to be my time, and they told me that, well, approximate altitude of 3,000. Well, if it changes every 1,000 and our altitude is going to 3,000, then we know that it is going to happen 3 times. So there we go. Let's see here. We got y is equal to 101 times 0.885 raised to the 3rd power, which is going to give me about, it's going to give me about 70.008, or approximately 70, and that is going to be the atmospheric pressure at 3,000 meters, and that is going to be 70 kilo pascals, and that's what we've been working with, and that is the atmospheric pressure. And it says, what is the atmospheric pressure at 5,000? Well, the only thing we're changing there is the number of times that it's going to be reoccurring. So it's going to be the same equation except for the number of time your x value is going to change. And so instead of 3 times, it's going to be occurring 5 times. And that is going to be, gosh, that should come up to 55. Basically, approximately 55 kilopascals when you put it into the calculator. And that is using exponential growth and decay. Things you're going to see for exponential growth, we're talking about population, bacteria, which is the population of bacteria growing. We often refer to compound interest or money as it increases in exponential growth. Some of the decay things you might see is radiation. We'll do a couple of word problems with radiation as the isotopes change. But again, a lot of scientific, a lot of real-world applications for using the exponential model for growth, decay. And so as we go through this, we talk about the difference between exponential growth and exponential decay. Well, the exponential growth is when I am taking the value that I have, 100% of my product, the 100% of that initial value, and I'm adding something to it. Whereas a growth decay is I'm taking 100% of what I have and taking something away from it. So hence right here, I had 100% of my item minus the 11.5%. So each time I'm taking 11.5%. That's why I have something smaller than I started off with. Okay, so, and then growth, of course, I'm taking 1 plus my rate, which is going to give me something larger than I started off with. And I guess to specify one last thing, we talk about the function, right? The exponential function, the initial value times the base raised to x. And we say that b cannot equal 1? I wonder why. Let's see, why can b not equal 1? Well, let's just plug some numbers in there. And we have y is equal to initial value of 5 times 1 raised to some power. Or maybe if it was the initial value of 1/2 times 1 raised to some time, well, here, any exponent of 1 is going to be 1, so it's just going to end up being 5 times 1, which will always be 5 no matter how much time you put in. And the same thing for this other example. 1/2 times 1 raised to whatever power is going to always be 1/2 times 1, which is 1/2. So that is the reason that we say a exponential function, the base cannot be equal to 1, because it would simply be a line, linear graph. So there you go. There you have it. That's the reason, the special rules for exponential functions.